Today, we are going to speak about rotational motions. We're going to continue to advance forward with kind of circular motion and now talk about rotation of rigid objects. And this is basically leading us right up to the exam, so this last topic. And after the exam, we'll continue to apply this. So it's not going to just end at the exam, it actually just gets somewhat more complex. But one thing that I wanted to do before we continue is we're going to have a short quiz. So here's the quiz. A wooden block A of mass 7 kilograms slides on a frictionless table when pulled via a massive string and pulley array by a hanging box B of mass 11.5. As shown in the figure, what is the acceleration of block A as it slides on the frictionless table? So go ahead, I'll launch the problem. Just kidding. We're not having a quiz. This was the hardest problem on the equivalent exam last year, or 2 years ago when I taught. So this problem is what you should expect to see in about a week from now. And you should all take pictures and try to solve it if you can. This has basically everything in one little problem, okay? So you're going to see problems of this caliber on the exam. There are interacting objects, there's kinematics, there's dynamics, there's Newton's laws, there are all three of them being used. This is the type of problem that you should expect to see, okay? So let's talk more about the exam. There's no quiz. I was just But we do have an exam next Friday, May 17th. It's right here. It's going to be similar to last time. Bring again the Scantron. I think the people that brought them had somewhat less of an annoying time. They had the peace of mind that they had one of these things in their hand. It cost cents. Bring your pencil, your student ID. All of this is the same. Calculator's okay. Nothing is programmable. And everything that you will need will be supplied on the exam. Okay? So the entire equation sheets. I will actually post, I think right now, on iLearn, I have posted this exam, the practice exam. Okay? What it looks like on iLearn is actually a final exam from who knows when, some ancient year. But there are certain questions that I've listed. I've listed all the questions that are relevant to the exam that's coming up. So when I described it, you don't have to do all of those. I mean, you're welcome to try any of those problems. But the ones that I've listed are the ones that are topics that are being covered up to now. So you'll see a huge number of problems that you can play with. One thing that I will also post this afternoon is a more complete equation sheet that you would see on the exam. So you'll see with the practice exam, a pretty full, it's like 2 or 3 pages of equations. I'll give you one that looks slightly more like what you'll see next week, so you can at least narrow it down. So all of this is now posted. The exam is obviously 1 week from now. Come prepared. Do as much as you can. Talk to your TAs, talk to the SIs. I know, here's one thing that I know Nick will be doing, is he will be looking at this practice exam. He may already be looking at this practice exam. He's going to start working through some of these problems himself, and he'll be there to assist you if you are solving these problems on the practice exam. Okay? So I think that's basically all we need to kind of get through it. The last piece is that we just have 3 kind of lectures of material. Here's what I would say. Today and Monday are much more important than, say, Wednesday. So I'm going to keep Wednesday essentially light so that we're not covering too much new ground. Most of the new stuff will be today and Monday so that you have at least some time to digest this newest stuff. Okay? So again, just like we've always done, we're just continuing to build. Yeah, question? Or you just sit up to the puppy. There's a puppy. Okay, is he well behaved? Like will he run away from you to me? No, hopefully not. Okay. I would try. Anyway, let's continue. So just like everything, we're building on existing things. So this exam, when you practice for it, when you study for it, you have to go back and study and practice kinematics. Because you can see problems in circular coordinates that look just like kinematics in one dimension. We'll see that today. So you have to build on what we've already done. So we're going to explore now how to understand the rotation of rigid objects and bodies. And then we're going to see that we can extend kinematics in 1 and 2 dimensions to the rotation of this rigid body. So all of that stuff that you threw under a rug after the first exam is going to come back in the next 2 lectures, and we're going to need it. So all of those things. You remember taking derivatives of position time graphs? That's all coming back, okay? It never goes away. Physics is real. Okay, well, let's talk about gravity. This is going to introduce us into this idea of rotating rigid objects. Here's an object that's rotating around our planet. We call it the moon. And we all know this, that if it's uniform circular motion, it's basically a few rules that we've set up. So one is that the speed, the tangential speed, is always fixed. Okay? So the moon basically moves around with a pretty well-defined tangential speed. The acceleration in uniform circular motion is in what direction? So uniform circular motion. Acceleration is towards the center. And what's the value? V squared over r, right? Always in uniform circular motion. So here, the force that provides that acceleration is actually the force of gravity. And we've talked about this, but we really haven't understood it. If I roll this wheel around, I can kind of model this thing, right? Imagine this point on the wheel is the moon, Earth is at the center. Do you see that it's the identical system to what I've shown, right? I have a point basically circling around a center axis, okay? We're going to study this all day today, but we're going to see that it is basically more general, and we can do a lot more to understand it. So again, what we know is that in uniform circular motion, I have an acceleration towards the center. It turns out that that value is basically some value g, but I've labeled it at the moon because it can be different depending on where we are. And we'll see that the number that we all know, 9.8 meters per second squared, only applies at the surface of our Earth, which is a fixed radius distance away from the center of the Earth. That number is just what it is right here, and not if I go 10,000 miles away, it's going to be different. Okay? So we know that there's a centripetal acceleration, and there's a simple model of this gravitational force, which is just that it's uniform circular motion with a fixed speed v. Okay? Now here's what Newton said about it, and I like this quote because it's very clear. Here's what he said. He was observing how the moon moved around our planet, and he said, I deduced that the forces which keep the planets in their orbs must be reciprocally as the squares of their distances from the centers about which they revolve, and thereby compared the force requisite to keep the moon in her orb with the force of gravity at the surface of the Earth, and found them an answer pretty neatly. Did that make perfect sense? Not at all, okay? Here's what he was saying, or here's what he eventually deduced in a very compact way, is that the force of gravity, or the force of this object 1 on object 2, depends on their relative masses, right? So in gravity, what we say is mass essentially attracts to mass. It's an attractive force. And so it goes as basically the scale of those masses. Think about it. If I have 2 really big planets, there's a much stronger gravitational pull than if I have 2 baseballs, right? It scales as their mass. And so you see that that's in this kind of prefab. There's a constant called Newton's gravitational constant, a number, and there's this dependence on distance that goes as 1 over r squared. When objects are really close, the gravitational force is really big. When r is small, the gravitational force is really large. When r gets really, really large, what happens to the gravitational force? It gets weak, right? I don't feel too much gravitational force from the next galaxy over from us, right? This is basically saying that that distance matters. Who kind of paid attention last year to the first observation of 2 black holes colliding? Yeah, I thought so. This is probably one of the greatest discoveries in our lifetime. And currently we have the Nobel laureate who was the discoverer of that in our department, Barry Barish. And he basically found, and a team of these people found that when objects are extremely massive, that this whole law breaks down, and you have these collisions of black holes when they get really close. And I'm not going to talk about it because it breaks down Newton's gravitation. It becomes basically Einstein's law of gravitation, or understanding of gravitation. But just like any other force, I can draw free body diagrams, and I can write down Newton's third law to show that the gravitational force of object 1 on object 2 is equal and opposite object 2 on object 1. So when I'm standing on Earth, and I'm being pulled by Earth's gravitational force, I also have a force acting on Earth, and I'm pulling on it. But do you remember these problems where we said that that's not really the important property, it's the accelerations that we care about. The Earth is going to accelerate me much more because my mass is tiny compared to its mass. And we solved this problem many times before. So I'm going to go through this slide pretty quickly, but this basically summarizes this force. We'll solve a few problems, but it's all just like every other force that we work with. The force of gravity is a constant, the product of the mass and r squared. I said this in the last slide. That number is called the gravitational constant, and it equals 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. It's just a number. I'm not that particularly interested in that number. And when you're solving these problems, this slide basically has all the information you need. When I think about mass out in space relative to Earth at some radius r, it's being pulled by the gravitational force of Earth. This is just like what we said when we're standing here. What gives us weight is the force of Earth on my center of mass. Okay? So the gravitational force on M due to Earth is what we typically call the weight. And you can write this force down as mass times this set of constants, which is the gravitational constant, the mass of Earth, which is extremely large, divided by r squared. Okay? So we know the radius that we are from the center of the Earth. We know the mass of Earth, we can estimate it, and this is a constant that we can measure. And it turns out where we stand at this radius from the center of Earth, we actually have this lump of constants equal to 9.8 meters per second squared. So that constant is not a fundamental physical constant. It's basically coming from the fact that we are at this radius from the center of the Earth. Okay? And you can actually, I won't show it here, but I'll put it on the notes. You can see that if I go up in a satellite, I'm going to feel a different g. And so you have this gravitational force acting on M, and it's basically just mass times g, which we've always said, but that g is actually a number that changes depending on how far away I am from this massive object like Earth. And then finally, at Earth's surface, we know the radius of Earth, and so we get this number, 9.8 meters per second squared, which you all, for some reason, remember. But it turns out that that's only at this radius from the center of the Earth. Okay? It's a very specific radius that we've chosen to get that. And that gives us this common thing that, again, you know that a mass of 1 kilogram has a weight of 1 kilogram times 9.8 newtons per kilogram, and it gives you something about 10 newtons. Okay? So just to give you a sense, 1 kilogram is something that you can kind of hold in your hand is about 10 newtons. So that's just coming from this factor. Okay? So this, you'll solve some simple problems with this. We won't dwell on it a lot. It won't be so important in this class, but you will see some basic problems to understand this force. You understand a lot about gravity already just from understanding weight and normal force. This gives us now the underlying physics. But now we're going to move on to what is actually very similar. This is the rotation of rigid objects. Okay? So before we were talking about essentially a small object, the moon, rotating around another object, the Earth, and this was kind of uniform circular motion. Now we're going to talk about taking an entire object, like this bicycle wheel, and just rotating the entire thing, right? So this is a rigid object. The mass that makes this thing up are fixed relative to one another. It's not liquid, it's not a gas. And if I spin it, I now have a rotating object, okay? Do you see that it's a lot like what we've been talking about? There's circular motion going on. If I pick a point, like this one at the end of the tire, that's just circular motion. It's moving through some angle per unit time, okay? The problem is that it gets complicated because there's mass everywhere. All of the points that make up this object are undergoing circular motion. And so we have to quantify how these behaviors can be understood. So we'll do that today and next time and continue with that. So here's an idea. Here's a rotating object like that wheel. The first thing we're going to do, this should look somewhat familiar, is I have an origin and then I have some point P, and I'm going to ask how it rotates. And we know, let me see if this works now. It didn't work before. Let me try it. Boop. Nope. Yeah, okay, good. So we know we had a coordinate system. We defined that the positive x-axis was our 0 degrees, and that positive rotation was in which direction? Counterclockwise, okay? So this object, I'm just going to, for a second, imagine that that point P is rotating in a positive direction, which we've defined, by some angle theta. It's at a radius r from the center, and it has an arc length s that it travels through, some distance. And we can basically understand this very simply. So the arc length is equal to the radius times theta, times the angle, right? So I can actually show you this. This is a strong statement that I have to prove in just a second. But let's assume that it's true. Then it tells us that the angle is then just the arc length divided by the radius, right? I just manipulate that equation. The unit is the radian, which is dimensionless. We talked a lot about this before. I travel through 2 pi radians in one circle, and that ends up being 360 degrees. So let me prove to you this first statement that the arc length is simply equal to r theta. It's actually non-trivial, and I want to make sure that we understand it. I think this will clarify quite a bit of why we say that. Okay? And this will actually help us understand this, I think, from a much simpler perspective. Okay, so let's think about for a second the rotation of a rigid object. Okay? You can kind of see, just make this like one at a time. Here's the same drawing. I've just drawn it, and I'm going to do some of these kind of handwritten notes so that you see how this can be understood in a slightly different way. I have this same point rotating in the positive direction, and I want to ask, what's the angular velocity? We're going to define this thing, angular velocity. And we first have to find the arc length that it travels. So remember, velocities are something like a distance over time. If I think about a velocity, it's a distance divided by a time. The angular velocity is something like the angle that I travel through per unit time. And we introduced this 2 lectures ago. But let's just understand this from a very kind of careful perspective. So who remembers what the sine function looks like? Right? We all remember this. It goes through this kind of oscillating behavior. If I take the sine of theta as a function of theta, I get what we often call a sine wave. Okay? Everybody's familiar with this. That sine wave goes back to the beginning of its shape after 2 pi. And then it just does the same thing. It goes through 2 pi again, oscillates through 2 pi, and continues. You'll study this a lot in later parts of this sequence. These are basically what make up waves. Okay? So if I look really carefully down here, I zoom in where theta is really small, you see that it's almost like a line there. Right? I can basically draw a straight line. In that neighborhood, it looks very much like a straight line. If I say that, this comes from calculus, near that point, if I change this function, sine of theta, the angle itself changes only a little bit, right? They change roughly proportional to each other. If I change theta, then my function only increases by a small amount. And so the limit, as theta is really small, basically gives me this relationship that the sine of theta at really small angles is basically just equal to the angle. Right? You could try this in your calculator. Take the sine of 0.0005 degrees, and you'll get an answer like 0.0005. Right? This is just coming from calculus. So if I assume that this is true, I can then draw a triangle, and I know you guys are getting less and less happy when you see triangles now. I can draw a right triangle here, and that triangle has some arc length s, which is a small value. I have a large radius, and I move through a small theta. And if I just look at the sine of theta, so SOHCAHTOA tells me that it's the opposite over the hypotenuse. The opposite is the arc length, the hypotenuse is the radius. And it allows me to, after some algebra, write down this expression. Arc length that I travel is just the radius times the angle. So if I tell you on this bicycle wheel that I've traveled through 90 degrees. Right? Let's say that in a problem, I say a point on a bicycle wheel travels through 90 degrees. Okay? And you know the radius of this is maybe 20 centimeters or 0.2 meters. Could you calculate the length that that point travels? Absolutely. It's 0.2 meters times 90 degrees in radians, which is pi over 2. And you would calculate, now I can do this with my hand, you're calculating this distance that I've traveled. Okay? Does that make sense? So it relates what is a normal coordinate, linear length, to now this angle of rotation. And this will be what comes into play in everything that we do for the next 2 or 3 weeks. And always go back to this. We'll come back to this more and more. So now, this is where, and last time I introduced this, but now we can define an instantaneous angular velocity. So rather than thinking about how that point travels along this length, I can think about how this point moves through some angle. I can say that in 1 second, I go through 2 pi. Okay? So I moved 2 pi radians in 1 second. That's 2 pi radians per second. That's what's an angular velocity. And if you do this using calculus, you see that we have to take delta theta over delta t, so the change in angle divided by time. And it's the limit as the time interval goes to 0. And that gives us d theta dt, which is just a derivative function. How does the angle change per unit time? And I can, with this expression, write down that it's d dt of s over r. So I'm just doing algebra. But what it gives me is what we saw before, again, last 2 lectures ago, is that if I have a constant radius, so again, this point on the wheel, its radius never changes, right? It's always about 20 centimeters away from the center. If that's true, I can then write down this derivative, 1 over r dx dt is just 1 over r times v, and I can write down the speed at this tangent, right? So the speed of that point at the tangent is just proportional to the angular velocity and the radius at which it's traveling, okay? So now again, this looks really familiar because we talked about lengths or displacements, we talked about velocities, and then we talked about accelerations. Now we have something that is called angle, right? We can change the angle that we travel through. We have something called angular velocity, which is how that angle changes with time, and then we can introduce angular acceleration, right? So in uniform circular motion, right, what is the rule of uniform circular motion? The speed is constant, and the acceleration is towards the center. Does that system have an angular acceleration? No. Who said that? Somebody said no. Why not? Because the speed is basically fixed. The angle is changing at a fixed rate. And so if I were to have an acceleration, here's an accelerating circular problem. I'm going to start slow. I'm going to accelerate, 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 accelerate. Do you see that what I'm doing is I'm speeding up the angle that it travels through per unit time, right? So we're going to introduce this concept a little bit more carefully, but it's all going to connect through this radius, right? If you see, the angular speed is just the speed over radius, or vice versa, depending on how you look at the algebra. So when we write this, the angular velocity is d theta dt, and there's a sign convention, and you know this already. The sign convention, a lot of you will come ask me this in a week. Which direction is the positive movement of this circle? Counterclockwise. It's this way. This is what we're going to call positive angular speed, right? This is my positive angular speed. My angle grows in a positive way in this direction. What is this? Negative angular speed, okay? So the convention of having these angles defined on the x-axis and growing is what's going to give us the direction of our angular speed, whether we're basically positive or negative angular speed. So now we can draw this somewhat complicated picture, but it's actually kind of embedding all of this information. This is something from the textbook. So this is how they embed all that information that I just went over. Does this not work today? There. So imagine again, I have this axle, just like I have this bicycle wheel. I rotate this thing from, through some angle, delta theta. The point that they're making on this picture is a really interesting one that we have to keep straight. You see these 2 points of tape that I put on the wheel? If I move them, do you see that they're traveling through the same exact angle, right? When I rotate this around, both have gone through 2 pi radians, okay? So any 2 points, no matter what the radius, they always move through the same angle, okay? So what would you say about their angular speed? The angle per unit time, are they the same? Is one bigger or is one smaller? I heard lots of different things. We'll come back to it. We'll see it in a second. Here's the answer. All points in the object have the same angular velocity regardless of the distance from the axis. What angular velocity does is it encodes how the angle is moving so that we don't have to keep track of individual particle velocities in the entire object. It simplifies our life because we don't have to think about all the different speeds that these particles are going. So let's try and see if we can get an understanding of this from your perspective. Let me launch this one. It's very simple. There are two coins that are rotating on a turntable. A turntable is just like the thing I showed you. It's just upright and it's a flat table. They sometimes call these lazy Susans, if you have one. Maybe your grandparents have one on their dinner table. Coin B is twice as far from the axis as coin A. Okay? So they're in two different radii. And which of these statements is true? The angular velocity of A is twice that of B. The angular velocity of A is equal to that of B. Or the angular velocity of A is half that of B. So go ahead and take about 30 seconds. Okay, so about 10 seconds. I have a lot of responses that I'll get. Okay, 5 seconds. I think I've got almost all of them. It looks like roughly who's here. Okay, I'm going to stop. Here's what I have. 77% said that the angular velocity of A equals that of B. Okay? We just said this. We defined right here, we said all points in this rotating object have the same angular velocity. So A and B have to have the same speed. Now, I just heard a conversation in the front. Somebody mentioned running races. This is good. If I'm running a race or driving in a car race, which side of the curve do you want to be on? The inside, okay? But I just said that this angular velocity, it didn't matter, right? They're both moving at the same angular velocity. So why does it matter that we're on the inside curve? Think about it. Here's the question. Here's the same exact situation. But now I'm going to ask about the instantaneous tangential velocity. This is the velocity right at the edge of these 2 points, tangent to the trajectory, right? So if these things are circling around, try to answer which of these statements is true. The instantaneous tangential velocity of A is twice that of B. The instantaneous tangential velocity of A is equal to that of B, or half that of B. So which one is moving faster for a fixed angular velocity? That's scary, right? Yeah. You're becoming a real nerd. That's what it's like. Back off. You don't want to go. Okay, about 20 more seconds. Okay, take a few more seconds. Okay, I'm going to stop. So this is typical, but what I'm getting is about 60-40 split. Okay, so 60% of you said that the velocity of A is slower than B. Okay, so at that tangent, it's slower than B. And then 40-ish% of you said that A is actually moving twice as fast as B. Okay, let's look at this slightly differently, just from a different perspective. Here's this origin. This is the origin of my rotation. And I'm going to rotate through some angle theta. Okay? This is what I'll call SA, SB. Do you see, wait, before we go on, do you see that these took the same amount of time? For A to move from here to here took the same amount of time for B to move from one to the other. Okay? Now, revisit the question and ask, if I travel much, much further in the same period of time, do I have to go faster or slower than someone who has to only travel a small distance? I'm going to redeliver it. See if this changes your answer. Okay, 10 more seconds. Okay, ready? Stop. Good. Here's what I got. 90% of you actually said C, that the instantaneous tangential velocity of A is half that of B. Now, if I was in a foot race or a driving race, why do we want to be on the inside curve? Because for the same angular displacement, to travel through that curve the same amount of angle, I have to travel a much shorter distance when I'm closer to the center. That means that my speed can be significantly lower and I can still travel faster around that curve than the outside driver or runner. Okay? So it has to do with the fact that in this case, for a fixed angular velocity, A's speed is half that of B. Okay? So here's what we're going to add to this. This is basically angular velocities. I think we have some sense of how they work. They move through some displacement per unit time. But here's the other one. And this is where it gets kind of tricky at first, but then you'll see that it looks just like 1D kinematics. So now we can add this idea that I can make this wheel speed up or slow down. Do we call this, if we have this wheel speeding up or slowing down, is it uniform circular motion anymore? No. We're going to completely ditch this idea of uniform circular motion and say that that's just a very special case. I can have any kind of circular motion with an acceleration. If the angular acceleration is 0, that's uniform circular motion. Okay? So we can add now more complexity to this. So angular acceleration measures how rapidly the velocity is changing. This should look really familiar. If we had 1D motion, velocity told us how fast the displacement was changing. The acceleration told us how fast the velocity was changing. Do you remember these graphs? We said that the velocity was the slope of a displacement time graph. The slope is the rate of change. The acceleration is the slope of a velocity time graph. Can you see that we should be able to say the same things? If I have an angle time graph, its slope would be the angular velocity. If I have an angular velocity time graph, its slope would be the angular acceleration. So we're building up this kind of same ideas that we saw before, but now just in rotation. So here's an example. Here's a motion diagram. Do you remember these from test 1? Little dots moving in similar intervals in time. What's going on in this wheel is that it's speeding up. I'm rotating in which direction? Is this wheel rotating positive or negative? Positive. Okay, good. Don't forget that. You'll lose it eventually. Most of you. It's just like old age, I guess. I'm rotating through the positive direction, but I'm speeding the wheel up, right? The wheel is increasing in angular speed. And so if I look at these points, the time intervals are the same, but I can move a greater distance each time because I'm going faster and faster and faster. We're going to define this angular acceleration as the change in angular velocity per unit time. And let's see if we actually can understand some very basic things. So going back to kinematics, see if that definition gives us a sense of how to understand this now in a circle. It's just like 1D kinematics. So take a minute. Here's the problem. The angular velocity we all said was positive, right? And it's increasing in speed. So it has an angular acceleration that's increasing. So I'm spinning a bicycle wheel. Which of the following describes this motion? The angular velocity positive, the acceleration positive, acceleration negative, or flip the sign of the angular velocity and alternate the sign of acceleration. Which of these choices is what this picture is showing as I rotate counterclockwise? Okay, so take about 20 more seconds. Okay, 2 more seconds. I got most of them in. Couple more, there you go. Okay, I got 80% of you said A, that the angular velocity is positive, we already said that, and that the angular acceleration is positive. How did you know that the angular acceleration was the same direction as the velocity? It's speeding up. I saw people say speeding. Do you remember when we said if I'm moving in 1D motion, I'm moving in the positive direction and I have a positive acceleration, what happens to me? I speed up. If I'm moving in that one dimension, just like this is old school now, I'm moving in that one dimension and I'm slowing down, what is my acceleration's direction? Negative. I still have a positive velocity, but I now have a negative acceleration. Do you see that this is exactly equivalent? I have a positive angular, I can even ask this, right? Here's a positive angular velocity. What's happening to the wheel? What just happened to the wheel? It slowed down. Which direction was the acceleration? The angular acceleration. It was opposite, or clockwise. You could say negative, right, by convention. So when I take a positive velocity but I slow down, that means I have a negative angular acceleration. Do you remember all these rules in 1D kinematics? If I'm moving in the positive direction and I'm slowing down, negative acceleration, etc. We have another graph that looks just the same. Here are those 4 basic possibilities. If I have, the easiest one, I think, to understand is basically speeding up in this counterclockwise way. This means that both are positive. My angular velocity is positive, the angular acceleration is also positive. And then all the other variants. So when you're solving problems, you should stare at this and kind of realize that if I'm going counterclockwise and I have an angular velocity that's positive, then the acceleration, angular acceleration, tells me if I'm speeding up or slowing down in that direction. Okay? So this will help you when you solve problems. Now we get to what I was saying earlier. If I plot for you, here's the thing. Math allows us sometimes to step back from the physics a little bit just to understand the world. If I give on an exam, do you remember there's a problem on the exam about a gene stealer running or something like that, and you had some displacement time? It's probably in your nightmares, right? This plot of displacement per unit time. The same rules apply here, where if you just look at the data and think about the mathematics of it, you can step back from the physics for a moment and then interpret what you get. Let's say I have an angular speed or velocity as a function of time that is increasing. If I just think of that in terms of this wheel, if I have an angular speed that is increasing, what's happening to the wheel? It's going faster and faster in the counterclockwise direction. I have an angular speed that is increasing. I could plot an angular acceleration time graph where I just take the instantaneous slope of that angular velocity time graph. So the mechanics of this are exactly the same as kinematics. I can take the slope of this graph to get the angular acceleration. But just like that, you can go backwards. And this was the part that you'll have to work on a little bit more because people struggled with this, I think, for exam 1. Is if I have, for instance, an acceleration time graph, the area under the curve gives me this angular velocity time graph. If I look at the area under the curve here, it's a positive value. That means that I have to have a positive slope. in my angular velocity. If the area under the curve is 0, it means I have a 0 slope in my angular velocity. So we now have these relationships, just like we did before. I can start with a displacement time graph, take a derivative to get the velocity time graph, take a derivative to get acceleration time graph, integrate acceleration time to go back to velocity, integrate that to go back to displacement. It's all the same. We've just now multiplied all of these things by a factor of radius, right? All of the math is otherwise equivalent. So before, when we had position, we knew how to do kinematics, and now we are just changing this. Now, instead of position, I'm going to think about how the angular position changes. And then I'm going to have velocity v, that is basically the rate of change of position, and I can redefine this thing angular velocity, which is the change in angle per unit time. And just like before, I had acceleration, I now have angular acceleration. Same exact formula. What was the next step? After we did kinematics, what came immediately following kinematics? What was the concepts that we introduced right after kinematics? Newton's laws. We started recognizing these things called forces, and they related to acceleration. Remember, the sum of forces is equal to mass times acceleration? What's the rotational equivalent of a force? Does anybody know? You're familiar with this. Torque. Everybody groans because it's hard to say. When you twist a wrench to tighten a bolt, do you see that you're applying a force at some fixed distance away from the center of the axis of rotation? A torque is a force being applied tangential to a circular motion. If I sum all the torques in a problem, and we'll see this next week, I get an angular acceleration. How can I make this wheel start turning? I can apply a force at this point. If I want this thing to go positive direction, which way should my force point? Down. Okay? We'll see that that's applying a positive torque. Okay? And we'll get to this. We'll define it more carefully. When I have a positive torque, I have a positive angular acceleration. So we're going to rebuild all of what we've done so far in one dimension, x's and y's, and now we can do it in this rotational degree of freedom. So let's go back really quickly for the last few minutes. Let's go back to 1D motion to make sure we get it. This one should be really easy, but it always tricks people. Let's see if you can go back deep into the recesses of your mind and ask this question. A lunar lander, a Martian lander is approaching the surface of Mars. It is slowing down its descent by firing its rocket motor. Okay? What are the signs of the velocity and acceleration? We're going to assume for this problem that up is the positive direction, just kind of the way you would conventionally. Up is positive. Which of these answers is true? The velocity is positive, the acceleration is positive, etc., etc. So take a few minutes. This is just old-fashioned 1D motion with velocity. Positive is up. We'll define positive as up. Okay, take about 10 more seconds. This is pure 1D motion. There's nothing to do with rotation in this. Okay, I'm going to stop. Get your answer in. Okay. So I said that up was the positive direction. Which direction is the velocity then? It's down, right? This is a lander. It's going down. So that already cancels out two of them. It's got to be negative. Now, if I'm going down and I'm slowing down, which direction is my acceleration? The opposite, which is positive. So it gives us answer C, which 68% of you got. Most of you got either C or D, but the pure majority was C. Wait, one more to see if we get it. Last one. Same basic problem. The fan blade that I'm showing here is slowing down. What are the signs of the angular velocity and the angular acceleration? So the fan blade is moving in which direction? Clockwise. So we have a convention for what that means in terms of the angular velocity. They take about 10 more seconds. I have a lot of responses, but not all of them yet. Okay, 3, 2, 1, get your, there's a few more left. Get him. Okay, before you run off, shh. So 80% of you said D, the speed is negative. That looks correct, right? It's moving clockwise. And the acceleration is positive. It's slowing down. It's positive.